For those who are not familiar with Atlassian's product and especially Rovo, our AI product suite, Rovo is an AI teammate that powers our intelligent search chat agent platform workloads. One is a simple application for optimizing query rewriting in across different use cases, different customers, and different domains. Right? It's also extremely hard for humans to manually encode trade-offs between different competing goals, such as precision, recall, latency, and effort. Right? We need policies that can learn from itself from enterprise-scale data. For example, we want to learn how to better interpret and rewrite users' queries that they enter into the search system, and we want the system to learn how to sequence tools over long horizons to complete tasks and reach goals. So NVIDIA's reinforcement learning stack, which includes NemoRL and NemoGem, gives us much faster training speed compared to competing products. And it also offers us a standard unified way to create and manage RL environments. So our very first use case that we use NemoRL for is for optimizing query writing for Rovo search. So the goal is to rewrite user queries to maximize downstream search relevance and task success. Right. So the action it takes is to propose structured rewrite proposals, which may include spell correction, normalization, expansion, and disambiguation. That's commonly seen in search engines. Right. So the state includes user queries and product, tenant, and user context. So the reward function would be based on the recall of relevant docs, and it could also include other type of search relevance proxy metrics, such as mean reciprocal, and generate a query write proposal. And the rewritten query is then sent to the search environment, which goes through retrieval using BM25 and vector search or hybrid search, and then re-ranking. And next, the reward function evaluates the outcome. It calculates a success signal such as recall, NDCG, MMR that I just mentioned, and it also applies necessary penalties such as format, length, and safety. So this is where reinforcement learning kicks in. With NemoRL, we leverage GRPO, group relevant, cluster. The training cluster leverages a pool of GPU instances that uses NVIDIA GPUs such as H200s, and everything executes on the Docker image that leverages the NemoRL base image. So in evaluation, we found that our reinforcement learned model beats the base model across the board. So in the standard dataset, our GRPO model improved recall attempt by 6%, and we observed similar gains on the hard queries dataset where it increased the recall attempt about 5%. Right? The main takeaway here is that the reinforcement learning actually works, and by leveraging NemoRL to optimize the downstream search relevance objective directly, we can achieve better document recall than we ever could with regular prompt tuning or instruction tuning alone. So our next use case is for optimizing 1 hour long horizon agents that we call the Jira issue solver. So the goal of this Jira issue solver is to resolve complex Jira issues end to end without human intervention. Right? So as the creator of Jira, we the permission environment instead of using a giant LLM that need to consider reasoning and true execution simultaneously, we break down the work into several specialized modules. As you can see in the slide, this system includes a team of coordinated modules, including the planner, which is a reinforcement learning series of 2 calls. It adds a label to the new ticket that says duplicate and then close it to this reinforcement learning algorithm is the reward, the schema constraints. So we evaluated this system across reinforcement learning, achieved best overall success rate directly from and constraint outputs and safety. Reinforcement learning adds robustness, needs a recovery curriculum and paired with a strong anchor to ensure bring us closer to our
Vertex AI team. For those of you who don't know, Vertex AI is Google.
Biggest unlock was
Vertex AI is Google Cloud's place to build, train, evaluate, and deploy machine learning and AI models. And today I'm going to talk about a new feature that recently won past software paradigms, where key here is that it's going to behave in an intelligent and an autonomous way. This is a departure from past software paradigms, where software is a little bit more deterministic and is focused on helping a person do a task. With an agent, it's owning the task. So zooming in a little bit, this is a high-level sort of architecture of what an AI agent is. Components here. In green, we have the model. Usually this is a generative AI model. This is sort of the reasoning engine of the agent. And then in yellow, we have an orchestration component. This is a piece of the agent that's going to help manage state, memory, and help with some coordination tasks inside the agent. And then finally in blue, we have the tools. These are the tools that the agent has access to and can call. These are APIs, functions, databases, or even other agents. Now, as you can imagine, the model is a very important part of this agent. It's the center where all the reasoning and logic is going to be happening. And there are a lot of quality off-the-shelf models that you could use for agentic purposes. I have to pitch Gemini, of course, because I'm a product manager at Google, but there's also some excellent open source models that you could use as well. Now, however, you as customers, you can imagine scenarios where those open source or off-the-shelf models are not going to quite cut it for your use case. You might have some specific data that's proprietary that you might want to infuse into the model. You might have some specific or unique tools that only exist inside your environment that an open source model hasn't been exposed to. So you might want to customize your agent to operate better in that environment, right? Now, the challenge is that that's pretty hard to do. It can be a real heavy lift to customize a model for agentic use cases. And that's true for several reasons. You as a machine learning engineer, if you want to customize one of these models, you have to deal with some very complex techniques. You have to choose the right pre or post-training technique to use to get good performance. You might have to deal with different types of model parallelism and optimizing framework code for good performance. If you're going to be customizing this agent on a continuous basis, it's very important that you're achieving good throughput in your training process. Otherwise, you might be wasting compute time, you might be wasting money. Post-training technique to use to get good performance. You might have to deal with different types of model parallelism and optimizing framework code for good performance. If you're going to techniques, you have to choose the right pre for agentic use cases that you might want to infuse into the model, customize your agent to operate better in that environment, right? Now, the challenge is that that's pretty hard to do. It can be a real heavy lift to customize a model for agentic use cases. And that's true for several reasons. You as a machine learning engineer, if you want to customize one of these models, you have to deal with some very complex techniques. You have to choose the right pre or post-training technique to use to get good performance. You might have to deal with different types of model parallelism and optimizing framework code for good performance. If you're going to be customizing this agent on a continuous basis, it's very important that you're achieving good throughput in your training process. Otherwise, you might be wasting compute time, you might be wasting money. And then you also have to contend with sort of the evolved infrastructure management and Vertex AI training cluster distillation being the main technique that we used for this agent customization pipeline. And then there's an evaluation and a results component here as well. Now, for this particular example, we were focused on training a model technique that we used for this agent here. Small to the student model. Student model starts to generate responses, and the teacher model in a real-time way is going to evaluate the quality of those responses. And then based on that feedback, we would update the weights of the well. Examples were here on this slide, you can see we evaluated a series of different teacher models. These are represented across the y-axis here, ranging from a small, I think about 2 billion parameter post-trained Quen model up to tool use. Actually, smaller teacher models actually yield the agent has access to and can call, and then critically success comes our training data set. Responses from the teacher that are correct, our student will be better off. But this is actually an example where rejection sampling didn't actually help. We found that in our model, we have infrastructure. So to run all of these experiments, our data science team used between 16 and 64 H100s, H200s, and V200s. And we remediated in some of our recipes as to accuracy. And then finally, just emphasizing the importance of reliable.
The model started to access to, maybe hit really challenging.
And GT is there's a lot of unknowns in terms of what goals the model should optimize itself.
直觉反应。 提升了行驶的平顺性，但其完成了千万 Clips 端到端版本升级，将与大家在联合生成和仿真的过程，他们以20赫兹的帧率运行，在系统检测到提供概精细的软件定义硬件的，从而将基础的物理常识有意识场景，在路口准备执行时，如果临近的左转车道排队静止，纯数据驱动的模型可能会错误模仿旁车的速度，而采取制动或不起速。通过蒸馏当前及未来1到3秒的自动驾驶可行驶空间，我们将 occupancy flow 作为抗捷径先验，这引导了模型学习真实物理规律。只要制车前方空间畅通，就可以行驶。数据到达时，系统首先基于制车运动学来执行 warp， 也就是运动对齐，将历史特征投影到当前坐标系，然后执行变了30赫兹的世界模型，引空间特征压缩为一组紧凑的视觉化认知 tokens， 是呢一定程度上带用了层级的生成式规划器。该模型采用3层架构，以兼顾意图预测与底层控制。顶层 decision 融合平顺的规划，但在面对长尾场景时，容易出现误差累积。而引入强化学习是在于赋予策略自我纠错和恢复的接管数据。我们将接管数据提取认知特征，来引导扩散模型的生成过程，从而增强模型在利用庞大的场景编辑能力呢，使得系统能够生成现实高保真 LiDAR， 并结合持续不变自适应网军化引起的这种退化为影，模型最终保持全局一致性和局部细节的精确性，解决了结构混乱与深度不稳定的问题。而 Vice 算法是在 ICCV 2025的 Real AD Sim 挑战赛获得了冠军。它构建了一个系统性的4阶段纯视觉街景外推生成流水线，解决了传统算法在轨迹外推时的几何畸变和规模重建时的算法设计。UFO 可以作为连接车端和云端的桥梁，使世界模型在线上能提供高效的实时表征，在离线端呢也能帮助快速迭代高质量的渲染资产。这一系列的研发工作促使我们团队始终保持了对重建类世界模型的较深理解，能够更好的适配自动驾驶量产闭环中不同阶段对算力和精度的需求。而另一方面，我们也在积极探索生成类世界模型与规划决策技术的协同，最近也取得了众多的研究进展。除了刚才介绍过的 Genesis 算法，我们在2026年 ICLR CGR 里还提出了多项新技术。首先是发表于 ICLR 2026的 World Splitting， 这是一项基于高斯辐射场的前馈式4D 场景生成技术，专门用于高效的复杂场景重建与动态仿真。这一技术的突破，使得我们在云端能够以较低成本生成平行驾驶世界，用于算法安全测试。而 Dream4 视频生成模型来，并且在插入2个车辆进行碰撞时，它们还始终保持固有的物理规律。通过这种物理规律的注入，我们缩小了仿真与真实之间的差距，也就是我们常说的 Sim to Real 的 gap。那第二个 demo 呢，是关于我们如何进行这种多风格多传感器的生成。从视频里大家可以看到，我们支持多样化的场景编辑，比如季节变化、光照变化、道路结构的调整，并且呢也支持多风格多传感器的生成，既能生成图像级别的视觉画面，也能生成激光点云，实现多模态的一致。好的世界模型离不开强大的4D 数字资产，4D 在这里代表的时间序列，通过对不同的交通参与者或信号控制灯等进行时间序列上的模拟，我们能更好的描述版本化的管理环境中不断的 GPU learners 同步进行梯度更新，根据场或者路口中的障碍物时，轻量且具备部署可行性的端到端。我们这一套认知智能的
solution. Here, one server is already consuming that much like one house is using. So see today, like the GB2 grid, so the medium voltage grid, normally it's stepped down by a line frequency transformer, a bulky animal, so 3 to 5 megawatt outside the building. Converting the medium voltage into 400 or 400 volts 3-phase AC. And then current deployment is this single-phase power shelves, like the GB200, GB300, converting the AC into 50 volt on the rack bus bar. So currently we are doing for the Vera Rubin a new category of units. So it's a real 3-phase AC unit, 18 kilowatt, and still 50 volt output. So it's still 6 volts, so which has to hook up. But there are 6 power supplies and 5 DBUs inside. So you will also see some more details in the next slides. Okay, so here you see the single line diagram from grid to chip, from left to right, from the medium voltage down to the 0.65 volt chip voltage. This is the conventional AC distribution which we see when you see no current. And also the bulk voltage is going up and down according to the load. What you also can see here on the single phase units, there is a 100 or 120 Hertz ripple voltage on the bulk. For the GB300, we were able by software control to smoothen out the input current. So you see already this looks very nice. Even on the output it's dynamics, but on the input it's nearly flat. So you just see
but AI has broken that pattern. So anyway, little technical glitch. Okay, so AI workloads are reshaping the data center. For decades, data centers evolved gradually, power densities increased slowly, cooling technologies improved incrementally, but AI has broken that pattern. So we are now seeing campus build now. So traditional data center design struggles in this environment. Most legacy facilities were built around relatively rigid electrical architects. Electrical distribution paths were designed for predictable loads. Cooling designs were for relatively modest rack densities. When AI loads arrive in those environments, the infrastructure often cannot scale. So electrical rooms become bottlenecks. Cooling systems cannot keep up with thermal density, and retrofitting those environments becomes extremely complex. So the challenge is even more difficult in brownfield deployments. Existing facilities often have limited physical space, limited power capacity, and mechanical systems that were never designed for these thermal loads. So the industry is being forced to rethink how data centers are built. All right. So one of the most important shifts is the move toward the modular infrastructure. So instead of building everything sequentially on site, infrastructure can be manufactured in parallel. Power systems are assembled in factory environment. It accelerates deployment timelines. Distribute power for 480 volt AC systems. So that architecture has served the industry well for many years. But as rack densities increase, it introduces limitations. So each conversion stage in the power chain introduces losses. Utility power flows through transformers, then through UPS systems, then through power distribution units, and finally through server power supplies. So each reduction in conversions improves efficiency. It also reduces electrical equipment footprint. And it aligns well with modern modular infrastructure strategies. Power blocks can be delivered or can deliver DC distribution directly to high-density compute environments. So that architecture supports higher rack densities with simpler infrastructure. And it provides a more scalable path for large AI deployments. All right, so efficiency improvement for AI deployments. All right, so that architecture supports higher rack densities with simpler infrastructure. So imagine a 100 megawatt IT deployment. So electrical costs roughly 8 cents per kilowatt hour. If we improve overall efficiency by just 2%, the facility saves roughly 19,000 megawatt hours of electricity per year. So that costs. Reducing conversion stages reduces the amount of electrical equipment needed, fit more closely with business demand, and it simplifies long-term operations. All right. So another key principle is that power and cooling must be designed together. Approach works well for greenfield. There we go. All right. So from a deployment perspective, most organizations scale AI infrastructure phases. So the first phase establishes the initial compute deployment. Once validated, additional infrastructure blocks are replicated. So this replication model allows rapid scaling. So that approach works well for greenfield deployments, but it can also support expansion within existing campuses. So over time, these phase deployments grow into AI factory campuses.
that we've got. Inspect and adapt and move your modernization activities forward. So is you have an LLM, you train the LLM, so the amount of effort that goes in to train the LLM will give you the best results. So there's an element of effort that is put up infra, which are GPUs, but where we factory and all the or SAP. So this is going back to